Graphing using transformations. To apply transformations, we need a function to work with. The following is a collection of basic functions that we will start with, and we will add more as the semester moves along. So we're going to call this our library of basic functions. On the left is the name of the function, so we have the constant function, just a horizontal line. The equation there is f of x equals b. Here you can see a numerical understanding, a table of values. So if you substitute in these x values, you're always going to get out the constant b. And over here to the right is some of the properties of the function. So the domain and range, intercepts, whether we have an even, odd, or neither function, and where the function is increasing, decreasing, or constant. So the next basic function on the list is called the identity function. F of x equals x. So we can see this linear function that passes through 0, 0, and a point 1, 1, 2, 2, 3, 3, etc. And here's the corresponding table of values. It's called the identity function because whatever you plug in, that's exactly what you get out, the same number. And again, here are some of its properties. Here are the next two functions we're going to add to our library of basic functions. We have the squaring function, which looks like this parabola. The equation is f of x equals x squared. Here's the table of values. So any x value we plug in, we square it to get to the corresponding y value. And again, here are some of its properties. We also have the square root function, f of x equals the square root of x. And here's its table of values. Notice that we're plugging in values that we can take the square root of without a calculator. So I can take the square root of 1, the square root of 4, the square root of 9, the square root of 16, because we do want to know specific coordinate points on all of our basic function graphs. And again, the equation and some of its properties. Next we have the cubing function, f of x equals x cubed, seen here, with its corresponding coordinate points. So we're taking x values and cubing them to get the corresponding y values. And again, here are some of its properties. We have the cube root function on our list of basic functions. So f of x equals the cube root of x. Notice, just like for square root, we're only substituting in values that we can find the cube root of without a calculator. So the cube root of -8 is -2. The cube root of -1 is -1, and so on, because again, we want to know specific points on all of our basic graphs. And again, here's the equation and some of its corresponding properties. And finally, on our list, we have the absolute value function, which looks like a v. Here is the equation for the absolute value of x, which of course takes in x values and makes them positive, right? And here's the equation and some of its properties. And the reciprocal function, f of x equals 1 over x, is this function here. These two pieces lie in quadrants 1 and 3. And when we take any x value, it's going to go in the denominator, so we get -2 gives us -1/2, and -1 gives us -1. 0 gives us an undefined value because we can't divide by 0, so that's where there are no values along the y-axis. And then plugging in 1, we get out 1. Plugging in 2, we get out 1/2. So you can see as we start to plug in bigger and bigger numbers, like 3, 4, 5, we're getting smaller and smaller values, 1/3, 1/4, 1/5, 1/6. We're just getting closer and closer to the x-axis, but it turns out we'll never reach the x-axis, so I actually don't intersect the x-axis as well on this reciprocal function. And again, here are some of its properties. Now this is a starting point for our basic functions, and again, as we move throughout the semester, we're going to add to this list of basic functions, and we really want to make sure we know the equation, the name, the graph, and specific points on the graph, because as you will see right now, we are going to apply transformation to these graphs to create new graphs. Examples of modifying an equation. Suppose we are given an original parent function y equals f of x. If we modify the function, we create a transformation of the parent function. Before we take a look at graphing these transformations, we're going to go through some examples of what it means to modify the function. So in this example, we're given the parent function y equals the square root of x, and we want to write a modified function given each written description of the modification. So let's say the written description is that we want to add to x or subtract from x. Then our newly modified function would look like, for example, y equals the square root of x plus 3. If we were told to add to x, then that value that's added, here I just made up plus 3, would need to be inside with the value of x, so in this case underneath the square root symbol. If on the other hand we're told to add to y or subtract from y, then this time the addition or subtraction has to go outside of the square root of x. So we're looking at something that's y equals the square root of x, and then on the outside something like plus 3. So this is an example of adding to y equals the square root of x plus 3. That plus 3 we think about as adding to the y equals, as opposed to the first one, add to x, we added 3 to the x that's underneath the square root. Now another type of description of a modification is we can multiply x by a number c greater than 0. So if we're multiplying x, it again has to be underneath the square root symbol. So my new equation, my modified function, would look like y equals the square root, and underneath the square root would have to be a number c. I'm going to choose 3. So 3 times x. So y equals the square root of 3 times x is an example of multiplying x by a number c greater than 0. And if we're asked to multiply y by a number c greater than 0, well, if I'm multiplying y, then it has to be on the outside of the square root. So I would have something like y equals the 3 I'm going to put on the outside as multiplied by the square root of x. So y equals 3 times the square root of x. So I'm multiplying y, so y equals 3 times the square root of x. And then finally, I could be asked to multiply x by a -1. So we are going to multiply the part underneath the square root where the x is by a -1. So y equals the square root of -x. And then multiply y by a -1. That means that that -1 is going to be on the outside multiplied. Y equals negative the square root of x. So here, basically, anytime we're affecting the value of x, we have to be with the x. So in this case, underneath the square root symbol. And if we're affecting the value of y, then that is going to be on the outside, either added, multiplied, outside of the square root symbol. Now these transformations of a given parent function include translations, reflections, and stretching and shrinking. So we're going to take a look at each of those. We'll start with translations. A translation is a vertical or horizontal shift to a given graph. In other words, up, down, left, or right. Let's start with vertical translations. Vertical meaning up and down. So here, how do we know we have a vertical translation? Well, if we add to y, that means we're going to shift everything up. If we subtract from y, that means we're going to shift everything down. So we'll take a look at a numerical understanding first. Suppose I have the x values -2, -1, 0, 1, and 2, and I'm substituting them into the parent function y equals x squared. So that means -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So numerically, let's see what happens if we try to substitute those same x values from -2 to 2 into the function, which I'm calling y1, equals x squared minus 3. Well, I'm going to go ahead and take -2 and square it. Well, that gives us 4 as we know, and subtracting 3 from that is going to give us a +1. -1 squared is 1. 1 minus 3 is -2. 0 squared is 0. Minus 3 gives us -3. 1 squared is 1. Minus 3 gives us -2 again. And then 2 squared was 4, and 2 minus 3 gives us 1. So now we can go ahead and compare our numerical understanding with the graphical understanding. Well, y equals x squared, that's a parent function, so we have the parent function drawn here, passing through the points -2, 4, and -1, 1, 0, 0, 1, 1, and 2, 4. And then the second function, y1 equals x squared minus 3, well, we have a few points, -2, 1, and then -1, -2, and then 0, -3, 1, -2, and 2, 1. So if we see those 5 points and think about connecting those together, the original function, y equals x squared, has shifted down 3 units because I'm subtracting from the y values. So if I'm subtracting from y, then everything moves down 3 units. Similarly, if I add to the y values, if I add on the outside of the function, then everything is going to shift up that many units. So in this case, everything is shifting up 3 units. So we don't want to have to draw a table of values every time. We want to instead recognize that we are subtracting from y, we are subtracting on the outside from a parent function that we already know how to graph, so it makes a quicker job of graphing this vertical translation, either down or up. Now let's take a look at horizontal translations, that is left and right. Now this is a little opposite of what we might normally think. So here, if we add to x, everything is going to shift left. Now normally we would think if we add to x, so on the x-axis, positive values are to the right. So we would think if we add to x that everything would shift to the right. But it in fact shifts to the opposite direction. Everything shifts to the left. And if we're subtracting from x, everything shifts to the right. So here we have a graph again of our parent function, y equals x squared. And if we're trying to graph the quantity x plus 3 squared, then since that plus 3 is inside with the x, we're adding to x, everything is going to shift left 3 units. And on this graph on the right, h of x is the quantity x minus 3 squared. So again, that minus 3 is with the x inside of parentheses being subtracted, so everything is going to shift to the right 3 units. Let's take a look at the next example. Given the graph of f of x shown, in part A, we're asked to graph y1 equals f of x and then plus 4 on the outside, and describe the translation in words. Well, since plus 4 is on the outside of f of x, that means that this is going to have to move up 4. So the translation in words description is up 4 units. So we're going to go over and take a look at the graph. So the graph looks basically like a W here. And we're going to have to think about moving each and every point up 4 units. Well, the best thing to do is focus on some key values, especially ones that pass through integers. So we're going to focus on the point -1, -1, move it up 4 units. So 1, 2, 3, 4. Now that coordinate point is at -1, 3. If we move up the point 0, 0, 4 units, I'm at 0, 4. And then if we move 1, -1, I'm at the point 1, 3. So focusing on those 3 key values will help me to construct that same shape. I don't want to change the shape. I just wanted to move everything up 4 units. And now I'm going to label it as the graph of y1, because my original function, we were told, is the graph of f of x. Now let's take a look at part B. So we want to graph y2 equals f of the quantity x minus 2 and describe the translation in words. Well, this time we have f of the quantity x minus 2. Minus 2 is with the x, so when something's with the x, we think right and left. but it's the opposite of what we would think. -2 actually sends us to the right 2 units. So everything is going to shift to the right 2. That's the description in words. And then again, we're translating the parent function f of x and moving everything to the right 2. So the point at -1, -1 will be at 1, -1. The point at 0, 0 will be at 2, 0. And the point at 1, -1 will be at 3, -1. And I want to do my best to retain the same general shape, that W shape. And then we'll label that the graph of y2. And then finally, part C is asking us to graph y3 equals f of the quantity x plus 1, and then -2 on the outside, and describe the translations in words. So here there's two translations going on. F of the quantity x plus 1, well, that plus 1 with the x is going to send us to the left 1. So we're going to translate left 1 unit. And the -2 that's on the outside, not with the x, is going to send us up and down. So since it's -2, it's going to send us down 2 units. So we're going to take the original parent function f of x and focus on those 3 values again and move them left 1 and down 2. So -1, -1 will go left 1, down 2, taking us to -2, -3. 0, 0 is going to go left 1, down 2, so we're at -1, -2. And then 1, -1 will go left 1, down 2 to be at 0, -3. So we'll go ahead and connect those, again trying not to change the general shape as best I can. And this is now the graph of y3. So here our parent function isn't one of our basic functions, but the graph was given. So here's some graph of f of x, and we can still perform these translations to it once we recognize which direction to go, either up, down, left, or right. Now let's talk about the next transformation, reflections. So reflections occur when I multiply by a -1. Now if I multiply x by -1, then I reflect about the y-axis. So here we have a graphical example. Suppose we are considering the function y equals the square root of x, so that passes through 0, 0, 1, 1, 4, 2. Well, if we multiply the x by a -1, so that's putting a negative underneath the square root and multiplying that x by it, so the square root of -x, then what the graph looks like is the mirror image over the y-axis. So instead of being in quadrant 1, I'm over here in quadrant 2. Well, 0, 0 doesn't change, but now I have -1, 1 and -4, 2. So that's what multiplying x by a -1 does, reflect about the y-axis, mirror image over the y-axis. If we multiply y by -1, meaning multiply on the outside by -1, that gives us a reflection about the x-axis. So once again, we have the square root function shown, 0, 0, 1, 1, 4, 2. And if we want to consider negative the square root of x, then that graph is down here in quadrant 4. The mirror image is over the x-axis. So 0, 0 stays the same. We have 1, -1. We have 4, 2. And then we can go ahead and connect those points to look like the mirror image of the square root of x graph. In our next example, we have the graph of some y equals f of x is shown. Describe the translations of each of the following, and then graph and label. So once again, this is not a basic function. This is just some function y equals f of x. It's over here in quadrant 1. And we're going to describe in words the translations and graph each of the following. So first we have part A, y1 is f of -x. F of -x. So since the negative is being multiplied to the x, that means this is going to be reflecting about the y-axis. Reflect about the y-axis. So we want to go ahead and construct the mirror image of our y equals f of x graph over in quadrant 2. That would be the mirror image over the y-axis. So 0, 0 stays the same. 1, 2 will be at negative 1, 2. And then we can see 2, 4 would be at negative 2, 4. And then we have 3, 6 would be at negative 3, 6. And then we have 6, 6 would be at negative 6, 6. So we'll go ahead and label those points and then go ahead and connect them so that we can create that mirror image on the other side of the y-axis. And we're told to label this the graph of y1. Now in part B, y2 is negative f of x plus 2. Well, the negative this time that's being multiplied is in front of f of x. It's not inside with the x. So since it's in the front, we are going to reflect about the x-axis. So we reflect about the x-axis, but there's a second part. We have y2 equals negative f of x plus 2 on the outside. So the plus 2 that's on the outside is going to shift everything up 2 units. So we're starting to combine these two different transformations, a reflection and a translation. So now let's go ahead and do this in phases. So first we'll reflect about the x-axis. So we're going to go ahead and consider the original function and flipping it down so that it's in quadrant 4. So 0, 0 stays the same. We'll have our new point at 1, negative 2, at 2, negative 4, at 3, negative 6, and then at 6, negative 6. But I'm actually going to connect those with sort of dashed lines because that's not my final answer. That's not quite y sub 2 yet. Because the next thing I have to do is shift everything up 2 units. So I want to go ahead and shift all of those points up 2 units. 0, 0 will move to 0, 2. And then 1, negative 2 will shift up to the x-axis at 1, 0. And then 2, negative 4 will be at 2, negative 2. 3, negative 6 will be at 3, negative 4. And 6, negative 6 will be at 6, negative 4. And then we will go ahead and connect those together. And that is now our graph of y2. Just a quick note, it is important that we perform the reflection about the x-axis first, because if we shifted everything up 2 first, we're also shifting up the x-axis. So it is easier if we think about reflection over the x-axis first and then shifting everything up 2 units. And now finally, for part C, our graph of y3 has to equal negative f of negative x. So this is telling me to do 2 different reflections. The negative in the front is a reflection about the x-axis. So we're going to reflect about the x-axis. And the negative in front of the x is also reflecting about the y-axis. So there's 2 different reflections going on. Now, we've already performed the reflection about the y-axis in part A. So we took our quadrant 1 graph and we flipped it over the y-axis, and that got me to quadrant 2. And so now if we want to perform both at one time, I'm just going to go ahead and think about reflecting my y1 graph down into quadrant 3. So I'm going to go ahead and keep 0, 0 because that stays the same every time. And then negative 1, 2 is going to move to negative 1, negative 2. Then I'll have negative 2, negative 4, and then negative 3, negative 6, and negative 6, negative 6. So we'll go ahead and connect those together, and that is my graph of y3, capturing both reflections. In this example, I want to identify the parent function that was transformed, and then write the equation for the graph of f of x shown below. So here, we're taking a look at an upside down V-looking graph. So what we have to do is recognize and identify one of our basic functions here. There's just other stuff that has happened to it, transformations that have happened to it. Well, the basic function that I see here is a v, or the absolute value function. So my parent I'm going to identify as y equals the absolute value of x. And now I want to think about all the things that have happened to it. So it's facing upside down, and that means that there was a reflection over the x-axis. So first I'm going to start by describing the translations in words. So we have reflects the x-axis, and it's also not centered at the origin, or the vertex doesn't pass through the origin. So the vertex is located at 1, -2. So that means the vertex has shifted to the right 1. So we have a shift to the right 1, and then that is also moved down 2. So I'm basically working backwards. I've identified what was the parent and what happened to it. It reflected the x-axis, it shifted right 1 down 2. Now it's my job to write the equation for f of x. So my function f of x is going to equal, we're going to start with a negative in the front of the function being multiplied, and that's going to take into account the reflection over the x-axis. We multiply by a negative in the front of the absolute value bars. And now in the absolute value bars, we're going to have x, and then we have to decide what we're going to go ahead and either add or subtract to x. Now since we move to the right 1, remember we think right and left, we think x, but we're moving to the right 1, so we're going to subtract 1. Remember, it's the opposite of what we think. Moving to the right is actually a -1 with the x inside of those absolute value bars. And then down 2 is subtracting on the outside, not with the x, right, with the y. So the down 2, the -2, will go on the outside. So we have in total, f of x is negative the absolute value of x minus 1 and then -2. In this example, we'll do the same thing, identify the parent function that was transformed, and write the equation for the graph of f of x shown. So here we have to recognize that the parent function shown is the cube root of x. So we'll go ahead and say that the parent function is y equals the cube root of x. But normally that passes through the origin, 0, 0, and that same value is now passing through 1, 2. So everything has been shifted to the right 1 and up 2 units. So focusing in on where the origin was, everything is shifted right 1 and up 2. And there is no reflection this time. So if we want to go ahead and write the function that represents this graph, f of x would be the cube root of x minus 1. So just like last time, right 1 goes with the x, and because it's right, we have to put -1. And that's underneath the cube root. And then since we're moving up 2, the +2 has to be on the outside of the cube root function. And in this example, we want to identify the parent function that was transformed and write the equation for the graph of f of x shown. Now the graph of f of x shown is a transformation of the parent function 1 over x. So the parent function that we'd have to be able to recognize is y equals 1 over x, but that normally lives in quadrants 1 and 3. So I normally have a graph that is in quadrants 1 and 3. But this one has a flipped shape here, so we can see that there has been a reflection that has taken place. And then also everything has moved up 2 units. So while the graph of 1 over x normally has a horizontal asymptote at the x-axis, that horizontal asymptote has shifted up 2 units. So the parent is y equals 1 over x, and there's a reflection. Now let's think about the reflection for a second. So here we can actually think about the reflection as over the x-axis or over the y-axis. And you'll see why in a second, but I'm going to consider it a reflection over the x-axis. And then everything does move up 2 units. So now in my attempt to write this equation, this function for f of x, I have f of x equals, well, if I consider this a reflection over the x-axis, then the negative that's multiplied would have to be in the front of the function. So negative times the function was 1 over x, and then up 2 is going to move everything up 2, so I'm going to have to add the 2 to the outside. So up to the plus 2 is going to be on the outside of 1 over x, not with the x. Now, I could have chosen to think about it as a reflection over the y-axis, so flipping over the y-axis, and what that would have done is kept my negative with the x. Well, if I put a negative in the denominator, I can take that negative and think about it on the outside, just based on how quotient works. So that's why it really doesn't matter how we think about this reflection as over the x-axis or over the y-axis, but the plus 2 does have to be on the outside since everything's moving up 2. Now the last types of transformations are stretches and compressions of a function. So suppose we're given f of x with c as a real number. If we take that value of c and multiply it on the outside of f of x, so c times f of x, then we either have a vertical stretch or a vertical compression, depending on what the value of c is. I have a vertical stretch by c if c is greater than 1. So a number bigger than 1, I'm stretching by that amount. But I have a vertical compression by c if c is between 0 and 1, like a half. So if I'm multiplying by a half, I'm actually compressing it, right? I'm halving it. But if I multiply by something bigger than 1, like 3, I'm stretching it by a factor of 3. So here we can go ahead and see this graph of f of x here, and if I consider 2 times f of x, I have a vertical stretch. So now that graph is stretched out up and down, so we can see that it's above the other function. And if I consider 0.5 times f of x, so I'm multiplying still, but by a number between 0 and 1, so I'm halving all of those y values. Now my vertical compression graph is underneath that original function because I'm cutting all the y values in half versus doubling all of my y values. Now, if I multiply by a c inside with the x, now I'm affecting things horizontally. So I would have a horizontal stretch by 1 over c by the reciprocal if c is between 0 and 1. So I would have a horizontal stretch by 1 over c if I now have a number between 0 and 1 like a half. I'd have a horizontal stretch by 2. So here is the graph of y equals x squared. If I have a horizontal stretch, now I'm thinking about things changing right and left, right? The x value is being stretched out. So I can see my parabola shape is fatter, is wider than x squared if I have a c value that's between 0 and 1. But I have a horizontal compression, so I have like a skinnier u shape inside here, if c is greater than 1. So if I have like the quantity 2x squared, that's actually going to be a more narrow parabola, versus if I had 0.5 x quantity squared, that's going to be a fatter u shape. In this example, we want to describe the translations in words to y equals the absolute value of x, and then graph each on the xy plane shown. So we'll start with a equals y1 equals 4 times the absolute value of x. Well, since 4 is on the outside, we think of it as affecting the y value, and if I affect the y, we should think vertical. So this is going to be a vertical stretch because 4 is greater than 1. That's how we know it's a stretch. So it's a vertical stretch by the number 4. That's the translation in words, a vertical stretch by 4. Now let's go ahead and graph it. We need to start by graphing the parent function y equals the absolute value of x. So 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. We're going to construct our v shape as our parent function. And then we want to go ahead and think about what it would look like if it stretched vertically by 4. We don't want to approximate this. We want to be very meticulous about this. If we're vertically stretching things, what's being affected are the y values. Well, 0, 0, if I multiply the y value 0 by 4, that stays the same. So we're going to have 0, 0 stay the same. But the coordinate point 1, 1, the y value is going to be multiplied by 4. So I had 1, 1, but now we're going to be up at the point 1, 4. So my new coordinate point will be at 1, 4, and at negative 1, 1, I will be at negative 1, 4. So if I connect those points together, I can see that my graph has been vertical, think up and down, vertically stretched. So my y1, 4 times the absolute value of x, is a skinnier v that's inside y equals the absolute value of x. And now in part B, we're being asked to describe the translation to y2 equals 1/3 times the absolute value of x. So here it's still vertical because I'm being multiplied on the outside. So I still have a vertical stretch or compression, but it's going to be a compression because 1/3 is between 0 and 1. So I have a vertical compression, right? I'm 1/3ing things. I'm making it smaller, compressing, vertical compression by 1/3. So because it's vertical, I'm affecting my y values. So what I'm going to do is come back to the original parent, y equals absolute value of x, and I'm going to think about affecting the y values and multiplying them by 1/3. So the point at 1, 1 would be now at 1, 1/3, would be at 1, 1/3. Well, I would say the easiest thing to multiply by 1/3 would be 3, and we can see that the absolute value of x passes through the point 3, 3. So a good point to really work with here, 3, 3, is now going to become 3, 1 because I'm multiplying the y value by 1/3. So I'm going to have the point 3, 1. And 0, 0 stays the same. So this is going to be one side of my new function, and the other side is going to have that symmetry going on. So I'm also going to pass through negative 3, 1, and negative 1, 1/3. So I can go ahead and plot those points. So I have 3, 1, and this was 1, 1/3. So we can actually see what is happening to specific y values on my transformed functions. And we'll label this as y2. In this example, we're going to describe the translations in words to y equals the square root of x, and then graph each on the xy plane. Let's start by graphing the square root of x. We know it passes through 0, 0, 1, 1, 4, 2. We want very specific points on these parent functions, so we have to be very familiar with the details of their graphs. Now we want to take a look at part A. y1 equals the square root of 4 times x. Since 4 is being multiplied to the x value, we're going to have a horizontal, either stretch or compression. Now, it's actually the opposite of what you would think. Anytime we're next to x, it's the opposite of what we would think. So instead of a horizontal stretch, because this number is greater than 1, it's going to be a horizontal compression. So it's going to be a compression by its reciprocal, which is by 1/4. It's going to be a horizontal compression by 1/4. So we're going to be affecting the x values since it's horizontal. So our coordinates on the original parent function 0, 0, 1, 1, 4, 2, we're going to think about affecting the x values. Well, 0, 0 stays the same. If I multiply the x coordinate by 1/4, I stay at 0. But 1, 1, the first coordinate, 1, will be multiplied by 1/4, so I'm at 1/4, 1. So this new coordinate point would be 1/4, 1. The y value doesn't change this time, the x value does. And then the coordinate point at 4, 2, well, the x value will change. 4 times 1/4 gives us 1. So I'm going to be all the way over here at 1, 2. So my coordinate point will be at 1, 2. And I will connect these points to get my horizontally compressed square root of x function. So horizontally, think left and right, how it's being squished inward more. And then for part B, I have y2 equals the square root of x over 2. Or another way to think about this is the square root of 1/2 times x. So I'm multiplying by x again, so I think horizontal. But whenever I'm by x, I do the opposite of what I would think. So instead of compression, even though 1/2 is between 0 and 1, it's going to be a horizontal stretch. And the horizontal stretch will be by the reciprocal. So the reciprocal of 1 over 2 is a horizontal stretch by 2. So we come back to our square root of x function, and we consider the original x values, and we multiply them by 2. 0, 0 stays the same. 1, 1 is going to become 2, 1. We're going to multiply that first coordinate by a 2, so 2, 1. And then 4, 2 is actually going to be off this xy plane because 4, 2 would become 8, 2. So I'm just going to go ahead and connect these two and know that it's going to be even thinner. It's going to go all the way to 8, 2, way over here. So we're going to have 8, 2 as a third point on my graph. And this is y2.